Welcome to the talk for Demystifying mmWave V2X towards robust and efficient directional connectivity under high mobility. My name is Song Wang. I am a PhD student at the University of California, San Diego. I'm going to start the presentation by introducing the motivation for this work. The emerging 5G NR V2X introduces new use cases such as vehicle platooning, extended sensors, and remote driving. These use cases help create an intelligent and safer transportation system while requiring high throughput data synchronization between vehicles and the road infrastructures. mmWave networking is a niche technology to satisfy such demanding applications due to abundant spectrum resources and high link capacity. However, the practicality of mmWave V2X has long been questioned. Due to high attenuation loss, mmWave radios have to use phased array antennas to form highly directional beams. Under a high mobility scenario such as V2X, the transmitter and the receiver may need to frequently search for the best aligned beam pair out of hundreds to thousands of candidates. The overhead for beam searching may easily become intractable. This is often considered as the most critical challenge for mmWave V2X. In addition, mmWave links are vulnerable to roadway blockages, including foliage, buildings, and high vehicles. Due to the sparsity of multipath, the blocked links may not be easily recovered. Finally, the directional mmWave beams open up new opportunities to achieve ultra-fine-grained spatial division multiplexing. However, the complexity of such extreme SDM may easily become unmanageable, especially under high mobility. To demystify the above challenges, we conduct a comprehensive reality check based on a mmWave V2X testbed, together with a large-scale 3D retracing simulation. Our experimental facilities aim to represent a 3GPP vehicle-to-infrastructure, so-called V2I network, comprised of roadside unit base stations, which is expected to be the dominating deployment model of mmWave V2X. Next, we introduce the key configurations of our testbed and 3D retracing. Our mmWave V2X testbed consists of 4 commercial mmWave radios deployed along a 1 km road segment. The nearby landscape represents a mixture of typical urban and suburban scenarios. The deployment complies with the definition of roadside unit, so-called RSU, in the 3GPP guidelines, which contribute to 97% of the coverage in V2X, as we show later. Each mmWave radio has 8 phase arrays arranged in a 2x4 layout. Each panel consists of 6x6 quasi-omni antenna elements. The phase on antenna elements can be reconfigured to form up to 128 different beam patterns, each corresponding to a beam-forming weight vector in a pre-defined codebook. Furthermore, we modify the firmware of the mmWave radio to enable fine-grained beam quality measurement. Our 3D retracing simulation framework takes large-scale, real-world 3D maps from OpenStreetMap as input and places large amount of moving vehicles on the road based on the SUMO vehicular traffic generator. We then use Wireless Insight, a commercial retracing simulator, to track the propagation effects of the mmWave signals, including reflections, scattering, and penetrations. Then we derive the channel and link characteristics. To verify whether the 3D ray tracing can faithfully reproduce the real mmWave channel, we feed a 3D model of our test site into the ray tracer and compare the simulation with the real measurement. These two figures compare the measured and simulated channel as the UE moves along the road. We see both the best beam index and per beam RSS match well across the trajectory. These benchmarks confirm that our 3D ray tracing simulation can accurately reproduce the mmWave channel profile. Drawing on the experimental results on both testbed and 3D ray tracing, we identify unique opportunities to simplify the mmWave V2X operations, including beam management, blockage recovery, and spatial reuse without sacrificing performance. Now we introduce our key insights. First, we investigate the network coverage when mmWave radios are deployed at the same density as 4G LTE. We observe that by co-siting with 4G base stations, 5G only covers 37% of the road due to the building blockages. Of all the covered areas, the base stations along road segments contribute more than 97%. This implies the co-siting with LTE base stations does not address the coverage problem in V2X, and to achieve pervasive coverage, more roadside base stations need to be deployed. It is well known that the mmWave channel is sparse for a given pair of TX and RX. In our experiments, we find the mmWave V2X channel exhibits sparsity even across locations. Unlike indoor mobile UEs, whose mobility is mainly induced by human activities, the vehicle movement is confined within fixed roads, and hence the angle of departures, the AODs, are limited to the only ones pointing at the links, and few outliers due to reflections. This implies that we can prune the beamforming codebook by selecting only those candidate beams within the AOD range, thereby reducing beam searching overhead substantially. With the pruned codebook, we observe a negligible 1.7% beam searching overhead on average across multiple scenarios, even with the standard beam searching protocol. It is generally observed that for indoor mmWave networks, higher mobility necessitates more frequent beam searching, which leads to huge overhead. In contrast, we find that V2X propagation paths change slowly for most of regions. As shown in the figure, the vehicle to base station distances are larger than 20 meters in the far region, causing the vehicle's relatively angular speed to the base station to be very slow. As a result, the beam searching only needs to be called occasionally to reduce overhead without sacrificing performance. We observe that even with a long beam searching interval of 100 milliseconds, only less than 5% of links suffer from RSS loss over 1 dB compared to the Oracle optimal beam selection. Whereas the small codebook can achieve optimal performance thanks to AOD sparsity and persistency, the beam selection in the near base station regions is still non-trivial. As illustrated in the figure, the AOD changes more quickly in the near regions, requiring shorter beam scanning interval. So even a smaller codebook needs to make a trade-off between beam searching overhead and RSS loss. In our experiments, we find increasing beam width makes the beams cover large angular range, and hence requires less frequent beam searching. We observe that a customized codebook with wide beams pointing at the near regions increases the average RSS by 13% comparing to the standard codebook under 100 milliseconds beam searching interval. Such customized codebook needs to be tailored in a site-specific way so that the beam widths are optimized based on the vehicle's typical speed. To investigate the severity of blockage in mmWave V2X, we examine the channel measurement in 3D ray tracing. We categorize the blockages into two types: recoverable blockages, which can be saved by strong non-live side reflection paths, and fatal blockages, where the link breaks once the line of sight is blocked. We observe, due to the relatively high base station deployment, only 8.5% of the V2X links in the urban scenario suffer from blockage, and 82.4% of the blockages are recoverable. The suburban and highway links suffer even less from blockage, 1% and 2% respectively, due to the lack of building obstacles. When a recoverable blockage occurs, the mmWave link needs to quickly identify alternative non-live side reflection paths. We observe that due to the AOD sparsity, the non-live side and live side paths AOD gap all fall below 20 degrees with only a few outliers. In particular, in the suburban and highway scenarios, the AOD gaps fall below 10 degrees for 50% and 99% of the recoverable links respectively. The result implies that to recover from blockage, a mmWave V2X link only needs to prioritize and search for alternative beams adjacent to the latest line of sight beam in order to reduce the beam searching overhead. On the other hand, to eliminate the fatal blockages, one simple solution is to raise the base station's height to overcome high blockages. We see in our experiments that over 99% of fatal blockages are saved by raising the base stations, regardless of the deployment scenarios. In case when raising the base station height is infeasible due to cost or spatial constraints, an alternative solution is multi-connectivity that allows UE devices to connect to more than one base station simultaneously. We observe that multi-connectivity can save 95% of the fatal blockages under normal traffic and 40% for dense traffic. Whereas the high directionality of mmWave radios reduce interference footprint, the dense deployment of V2X base stations may still exacerbate inter-cell interference. An intuitive way to avoid interference is using RX beamforming to amplify the desired base station signal while suppressing others. We see in our testbed experiments that the inter-cell interference becomes negligible after RX beamforming. We further cross-validate the result in the simulated scenarios. We see RX beamforming effectively reduces the interference, improving SNR by more than 30 dB on average. However, RX beamforming does not eradicate all interference because of the imperfect beams and the interference signals coming from the same direction as the desired signal. In contrast, we observe that the transmit beamforming rarely offers any opportunities to achieve high link RSS for desired UEs while maintaining a low interference for others. 3GPP NR base stations adopt multiple phased array panels for gain or coverage improvement. Recent work pointed out that such an APA structure may suffer from a co-phasing effect, where the signals on different arrays combine incoherently. In our testbed experiments, we observed that although the co-phasing effect creates significant fluctuations in link quality, it does not affect beam selection because it creates the same RSS loss across all beams. Therefore, the beam selection scheme can keep its simplicity and does not need to be changed to accommodate co-phasing. mmWave MIMO is a major feature in 802.11ay and the upcoming 3GPP-NR. Standard mmWave MIMO requires multiple RF chains and a sophisticated hybrid beamforming scheme to serve multiple UEs without interference. An alternative and simpler way of harnessing mmWave gain is to direct steer different phase array beams to different UEs. We find that due to the large UE spatial separation, simple beamforming to different UEs without hybrid beamforming achieves similar performance. We also observed that simple beamforming approach performs better at UE selection than traditional condition number-based UE selection in hybrid beamforming, since the former takes into account not only channel orthogonality, but also the link RSS. In summary, we presented a real-world measurement and large-scale 3D retracing-based characterization of mmWave V2X networks. Our experiments debunk some common myths on beam management and blockage, discover some unknown issues in spatial multiplexing, and show that mmWave V2X works even with simple solutions. Our 3D retracing source code has been released on our website. Please refer to our paper for more details. Thanks for your attention.